Let us wait for a few minutes, let others join. Okay, let me start. Let others join. Very good morning. Let us now talk about eye diagram. The other name is eye pattern. Either you can say eye diagram or you can say eye pattern. We all on a sudden this topic. Eye diagram or eye pattern is a graphical representation used to study ISI. It is about ISI, intersymbol interference, how much ISI is present, and the effects of ISI in digital transmission. Let me repeat, eye diagram is a graphical representation used to study the quantity, how much ISI is there. Ideally, ISI has to be zero. Ideally, ISI has to be zero, but practically ISI will be there. Practically ISI will be there, interference will be there, and then its effect on the digital transmission. And why is it called as eye diagram? We will see. Because this diagram resembles human eye. Since this diagram resembles human eye, this is called to be eye diagram. This is just a two-page PDF. Then we will go to the yesterday's PDF. The same thing as is the performance of a system in operation. So it is an eye diagram. Just Vignesh Khanna, can you go to the next page? So that you can have an idea. Listen, students, this is the eye diagram will be like this. The eye diagram will be like this. Now let us go for its description. Let us get to know about the eye diagram. What is it? Vignesh, can I go to the previous page? Okay. And then why is it called eye diagram that we have seen? It is between a pair of rails, something like the parallel lines, and it is used for several coding schemes. You can use it for PAM and then PSK, any digital modulation, and then it is done for the time domain signal, and then we have to overlap for the we have to go for a binary sequence. We cannot just we have to go for a binary sequence. I mean the message, the transmitted signal, we have to go for a binary sequence, ones and zeros. Then we have to go for an overlap, and it is being sampled. And where is it seen? Where is the eye diagram seen? It is seen in oscilloscope, CRO. It is seen in oscilloscope, CRO. How? We have to apply the received signal in the vertical plate, that is the OE plate. We have to apply the received signal in the OE plate, and we have to apply, what about the X plate? We have to apply a sawtooth waveform, and then from the eye diagram, we can note down three things. The eye opening, whether the eye is fully open, say at time when we meditate, we close our eyes, is that right? So now, till now we saw about the background, so do not worry too much. You can see the eye diagram in the CRO by applying the received signal in the OE plate, and then we have to look at eye opening, and then eye width, eye opening, eye width, and then eye overshoot or undershoot. The first thing is opening, whether the eye is fully open or it is closed. So the eye opening, that talks about ISI, how much ISI is present. And then the eye overshoot or undershoot, it talks about the peak distortion. Peak distortion, and then eye width, the width of the eye. I will differentiate that. Eye opening is like that is height peak to peak. It is about the vertical. Eye width is horizontal. Eye width is the horizontal. Eye opening is vertical. Eye width talks about the timing, synchronization, and then jitter effects. So let me repeat. Eye opening is vertical, peak to peak, like maximum. Eye width is horizontal. And then the figure shows eye diagram for, and then the next one is for, so they have taken this from some book, Free Space Optical System. And then go to the next page. And this is for Emery signal. Emery means not binary scheme. Even this could be a QPSK. Yesterday we spoke about BPSK. Even this could be QPSK or 16 QAM or anything. Vignesh Khanna, thanks for sharing. Let us go to the yesterday's PDF. Vignesh Khanna, thank you. You can stop sharing. Aditya or Karishma, can you share yesterday's PDF? Aditya, can you share? Okay, no hurry, Aditya. You can take your own time. Students, any doubts so far? We will see in detail. Just it's only an introduction. Now we will discuss in detail about the eye diagram. Let us call this to be eye pattern or eye diagram. Even in our lab, in our Center of Excellence in Wireless Communication, we have a what? Advanced equipments. We have advanced equipments to see eye diagram in a simple way, not in a to study about eye diagram, like a demonstration, demo. In our Center of Excellence for Wireless Communication, we can see eye diagram in a very simple way. Aditya, did you share? Okay, Karishma, can you share? I think, okay, Aditya is joining back. Karishma, can you share? Okay, Aditya is sharing. Okay, fine. Students, listen. Even doctors, when you go to hospital, doctors, they use so many scans to know about the abnormalities, is that right? Similarly, we are using eye pattern to study about ISI and its effect. Can you minimize the right tab, Aditya? Right side? Okay, perfect. Go to that eye pattern. Okay, let us start now. They talk about the synchronization between the transmit and receive filter to okay, eye pattern is simple. It is very simple to generate. Is because it's a easy tool. It is a visual indicator, simple and then visual indicator. Next one. Aditya, next page. And then regarding timing feature from the eye diagram, you can know about the optimum sampling time, like at which time instant I should take the sample. Say now we are going for I'm going for the lecture. I should know when I should take. Say somebody want to observe or monitor or record. I can say what is the right time. Now the strength is only 80. So I can say just you can record by something like 9 o'clock. So what is the optimum sampling time? The time instant at which the sample must be drawn, and then regarding zitter, and then timing sensitivity. So it is about the receive filter. You know about sensitivity. So timing sensitivity is the rate at which the eye pattern is closed. Listen, it is like AC signal. So the eye pattern will not remain constant like DC. You have to understand that. The eye pattern will not remain constant as at like DC. So the eye pattern will keep on varying. The eye pattern will keep on varying so that the rate at which the eye pattern is closed, it talks about timing sensitivity. Then we talk about zero crossing zeta. So let us talk about that later. Next one. So now what we have done is let us go for a binary signal, binary data sequence. We have a binary sequence. Let us go for the level something like S plus 1 and then minus 1 you can see. So you have a sequence 0, 1, 1, 0 and so on. What about the level? So you have a positive level and then you have a negative level and then the bit duration. When you look at a single bit, the bit duration is TB. So how will its eye pattern be? The corresponding eye pattern will be like this. The corresponding eye pattern will be like this. So when you look vertically, like vertically, the peak corresponds to plus 1, the valley corresponds to minus 1, and then the width, okay, let me tell you correctly, the height or the eye open, the height, the total height corresponds, the height corresponds to the level. The height corresponds to the level. The height corresponds to +1 and then -1. The width corresponds to bit duration. Is that, note down that the eye width corresponds to bit duration. The eye opening, that is the height, corresponds to the level. Next one, next page. Okay. And then we spoke about the distortion. So regarding the distortion corresponds to the eye. What did we see? Vignesh Khanna, do you remember the distortion? We spoke about the eye width and then the eye opening. What was the second one, second parameter? Vignesh Khanna, do you recollect? What was the second one? The distortion corresponds to, you can refer that. Okay. These are the two extreme cases. So the eye opening, if the eye opening is unity, eye opening is full. If the eye opening is full, what does that mean? 0 ISI, because that is, we have got two level in our binary sequence, in our transmission. If eye opening is unity, ISI is 0. If eye opening is 0, that means completely closed eye. The second extreme case occurs when the effect of ISI is severe enough, we cannot say infinity, is severe enough for some upper traces in the eye pattern. So what we have to see is, when eye opening is unity, ISI is 0. When eye opening is 0, ISI is severe. It is the worst case. Say we have got the noise, maximum noise. So eye opening is 0 means what? ISI is worst, severe. Next page. Now you can see, like, eye pattern is between the parallel rays, between two parallel rays, and then interpretation of the eye pattern for baseband binary data. As I told you, the height corresponds to eye opening. And then this when you look at the eye pattern, the peak, the peak, say it is like now it is almost like a triangular waveform, like a superimposed triangular waveform. The peak, the time instant at the peak is the best sampling time, optimal sampling time. The time instant corresponding to the peak value is the optimal sampling time. So that you can note time interval over which wave is best to sample. So do you understand? It is like two superimposed triangular waveform, and then this crossing is when it crosses, that corresponds to distortion of 0 crossing. What is the distortion? Then you can look at the margin over noise. What is the noise margin? And then the slope. The slope corresponds to sensitivity to timing error. We will discuss that in detail, don't worry. So the slope, that is, what did I say about the sensitivity? The rate at which the eye pattern gets closed. So the slope corresponds to sensitivity, and then this, it is like symmetric. The eye pattern is symmetric, is that right? The eye pattern is symmetric. Half of the height corresponds to noise margin, and then this the gap between the peak corresponds to distortion at the sampling time. Distortion at the sampling time. Okay, go to the next one. Just now we spoke about noise margin. In a noisy environment, what happens? The eye opening is 1 minus d peak. Can you go to the previous thing, Aditya? Did they mark d peak there? Oh, distortion peak, I guess. So let us see. Let us see. Go to the next page. Aditya, go to the next page. The extent of eye opening at the optimum sampling time provides a measure of the operating margin over additional channel noise. So let us see. So you have the eye opening. It is the peak distortion. That's correct. What is this D peak? Capital D stands for distortion. This is the peak distortion. So they have gone for various cases. Zero peak distortion when the eye opening is unity. That's correct. When eye opening is unity, ISI is 0. When eye opening is unity, ISI is 0. Zero peak distortion. When eye pattern is completely closed, what does that mean? We said severe ISI. Severe ISI, that corresponds to unity peak distortion. So the idealized signal component. And then this one we discussed earlier, ISI. So do not worry too much. So students, you see here, just I'm explaining you in slide. Only when you visualize this in the lab, you can try to relate. So you see that eye pattern is between two parallel rails, and then like between +1 and then -1. The eye pattern is between the levels +1 and then -1. And then when eye opening is unity, opposite. Eye opening is unity, 0 ISI. When eye is closed, closed because of what? Closed because of severe ISI. The next one. So now we are discussing about the binary scheme. Binary coding schemes or modulation schemes. Illustration, the peak distortion and then the eye opening is +1 and then -1. So you can see beautifully here, I told you about the symbol duration TB, the width, the eye width. The eye width correspond to symbol duration TB, and then yes, you can know about the signal level. Yes, the signal level is not the complete one. It is only for one triangle. So please understand, the signal level is not for that superimposed one. It is only for one triangle. It is only for one triangle, not the superimposed triangle. And then the eye opening, that is the top one, that is this between the peak, the gap between the two peak. The gap between the peak correspond to 2 into peak distortion. And then eye opening is this is the eye opening. Okay. Aditya, go to the previous page. Let us revisit the formula for S. So the eye opening is 1 minus peak distortion. The eye opening is 1 minus peak distortion. So peak distortion is 1. Okay, 1. Again, let us not confuse. Eye opening is 1 minus peak distortion. Go to the next page. Yes, we have to subtract the peak distortion. We have to, for the eye opening, we should not take into account those two, the gap between the two peaks. We should not take into account the gap between the two peaks. So this is plus 1. So the eye opening is 1 minus the peak distortion. The next page. So they are talking about the maximum ISI, the peak distortion, and then the eye pattern for Emery transmission. Emery is M can be 4. It's not binary. It can be powers of 2, 4, 8, 16, 64, and so on. So let us not concentrate on this. Just go to the next one. So this will be quite messed up. So the idea here is yes, the top one is for, so they did not mention maybe this is for PAM or whatever it is. The top one is for M is equal to 2, and then the bottom one is for M equal to 4. Even M equal to 4, just you have got 4 things, is that right? Something like 4 eye patterns. So this is a single eye pattern. This is like you have got 4 eye patterns superimposed. 4. M equal to 4. So what do they say? How did they mark the y-axis as a response? They have marked the y-axis as the response. X-axis the time. X-axis time in second. Y-axis the response. Response between plus 1 and then minus 1. So they did not mention which coding scheme it is. So they say with no bandwidth limitation. So they assume something like infinite bandwidth, or there is no bandwidth constraint. Just you can concentrate in the binary scheme. And then what we discussed so far is ideal. So practically it won't be like a ideal triangle. So practically this will be like this. So do not worry too much if you refer some more content. If you look at animation, things will be clear. Go to the next page. And then this is for, with bandwidth limitation. That is without bandwidth limitation. This one is with bandwidth limitation. What is happening for M equal to 2 and M equal to 4 is there will be a change. So let us not worry about now. Let us look at the case with no bandwidth limitation. Next page. Just I will finish within another 10 minutes. Now only I'm feeling better, not completely okay. So we spoke about this transversal filter, delay lines in the equalizer. Next one. Yes, I showed you this diagram already. And this corresponds to the delay and then the weights. You have a summer. This is the tapped delay line equalizer. Next page. The other name is transversal filter, not traversal filter, transversal filter. Next page. So they have gone for the block diagram representation. So this we have seen already. Next one. So let us not worry about these equations. Next one. Yes, we spoke about the zero forcing equalizer. It is about the coefficient matrix. For the zero forcing equalizer. Next one. And they have gone for a problem. Yes, I think you would have done that in the lab. In the lab, you would have done this one. This is about, I think you would have done this in the lab. A zero forcing equalizer is to be designed using 3 taps. Assume the input pulse. This is a pulse. I think you would have done this in the lab using a matrix method. Next one. Yes. So this is about the solution, like you have the pulse, and then now you want to find the coefficients of the filter. You want to find the taps. You want to find the taps, and then ideally this has to be 0, 1, 0, the response for equalization. You would have done this in the lab. So this is for three coefficients. This is for three coefficients. Trivial is 2. Trivial is, you cannot go. One is quite confusing. Trivial is 2. This they have gone for three coefficients. So this is just what they have done. They have gone for the inverse matrix. If I'm correct, they have gone for the inverse matrix. Is that right? They have gone for the inverse matrix. So then they got the filter coefficients. Next page. And then the receiver, it is about the receiver coefficients. We will discuss about the PN sequence later. Next page. Just now we spoke about ISI, I pattern, everything. Next page. Go to the previous page. Let me highlight a point. Okay. ISI is signal dependent. ISI is signal dependent phenomenon. It disappears when if you switch off the input. If you switch off the input signal, ISI will not be there because ISI is signal dependent. This is an important point to be noted. When you switch off the transmitted signal, ISI will go. But what about noise? Even you would have done this tried this in the electron devices lab or analog electronics lab. Noise is always there, regardless of whether the input is, even when you switch off the input signal. So let me repeat. Think about the LIC lab or the electron devices lab or analog electronic lab. When you switch off the signal generator, what output you get in the CRO, that is the noise. So they have gone for another corrective measure. The corrective measure is channel equalization. Next one. Students, with this, let me close. So in the next class, I think we have a class on Saturday. I will confirm. You can also check with your tutor. I think we have a class on Saturday. So any doubts so far? Any doubts or questions? So do not worry too much. Have an idea about I pattern, I diagram, and then concentrate for the binary case. Binary coding scheme, binary case with no bandwidth limitation. I pattern for binary case with no bandwidth limitation. Even you can look at the ideal triangular waveform, nothing wrong. You can look at the ideal triangular waveform, have an idea about the I opening, I width, and what was the second one? I opening, I width. Just a minute, let me check. Okay, let me ask you this as a question. In the first PDF, we spoke about three things to be noted in the I pattern. I opening, I width. What was the other one? Just now I cross-check. Can one of you reply? Vignesh Khanna or others, can you reply? Vignesh Khanna or others, can you reply? What is the other one? Eye opening, eye with, what is it? Yes, Karishma is correct. Eye overshoot or undershoot. Eye overshoot or undershoot, that refers to distortion. So what is that overshoot or undershoot? Something like that sphere, there is a sphere. What is that? Semi-sphere. There is a semi-sphere above the top horizontal, above the top rail. There is a semi-sphere. There is a semi-sphere above the top or the bottom rail, top or the bottom vertical line. So that corresponds to eye overshoot. That talks about the distortion. So with this, let me close. In the next class, we will discuss about digital modulation schemes. Students, any other doubts? Anything else? Vignesh Khanna and Aditya, thank you for sharing the screen.